back to The Explainer. So today, we're tackling a concept that traditionally makes physics students literally break out in a cold sweat. We are going to demystify Faraday's law together, taking it all the way from frantic margin scribbles to complex integrals, just to see how intuitive it can actually be. Let's dive in. You know the feeling when you flip open a textbook and just get hit with a wall of terrifying calculus, dense text, and those frantic, desperate margin notes? Yeah, we've all been there. But hey, don't let it intimidate you. We are going to decode this whole thing completely. And the best part, we're actually going to use those frantic student scribbles as our secret decoder ring. Just so we don't get lost in the weeds, here's our quick roadmap. We'll start with the spark of induction, move on to defining electromotive force, and then decode magnetic flux. After that, we'll hit the math of Faraday and wrap it all up by comparing static versus induced fields. 5 easy steps. Let's do this.
All right. Section 1, the spark of induction. Changing magnetism creates electricity.
So, the absolute core of this whole thing boils down to one fundamental rule. Whenever the magnetic flux through a loop changes, an EMF is induced. That right there is the fundamental phenomenon of electromagnetic induction. Faraday basically figured out that a time-varying magnetic field, meaning magnetism that's actively changing over time, actually creates electric current in a circuit. It's this profound, almost magical connection between magnetism and electricity. But to really grasp how it works, we need to pin down exactly what the textbook means by these specific terms. Which brings us to Section 2. Defining electromotive force. What exactly is EMF? Before we even touch the calculus, we've got to meet the first major character in our story, and that's the induced electromotive force, or EMF for short. The formal textbook definition tells us it's the work done per unit charge to produce the induced current. Now, pay attention to those two key words, work and charge. At its heart, EMF is fundamentally about the energy, the actual physical work required to move an electrical charge. And here is where it gets really interesting. If you look at how a student broke this down in the margins of the textbook, it's pure gold. While the printed text is super dense, the handwritten notes just say EMF equals work over charge and voltage equals W over Q. Look at how beautifully simple that is. It takes this scary, abstract physics concept and turns it into a basic fraction you probably learned in middle school. Now, let's see how that simple fraction builds into the heavier math. Okay, let's trace through this brilliant little piece of marginalia step by step. We're going to watch basic mechanics evolve into that intimidating closed loop line integral from equation 1.2. First off, remember from your intro physics classes that work, or W, equals force times distance, represented as F dot dl. Next, force per unit charge, so F over Q, well, that's just the definition of an electric field, E. So if we want work per unit charge, which is W over Q, our trusty definition of EMF, we just substitute our terms, and we get E dot dl. And finally, because we're moving this charge all the way around a closed loop, we sum the whole thing up using an integral, resulting in epsilon, our EMF, equals the closed loop line integral of E dot dl. Suddenly, that terrifying equation isn't so scary, right? It's literally just work over charge. Moving right along to Section 3, decoding magnetic flux, the phi sub m factor. So, magnetic flux. It's represented by the Greek letter phi with a little subscript m, and it's simply the amount of magnetic field, capital B, passing across an enclosed surface, capital S. Picture a wire loop, kind of like a hula hoop, and imagine the magnetic field lines are wind blowing right through it. The flux is just measuring how much of that magnetic wind is passing through your hoop. The text represents this mathematically as equation 1.3, where flux is the surface integral of the magnetic field. And this actually brings up a really surprising geometric fact pulled straight out of a little note box in the text. It points out that in 3 dimensions, infinitely many surfaces can have the exact same boundary. Going back to our hula hoop analogy, the flat space inside the hoop is one surface, right? But imagine dipping that hoop into soapy water and blowing a massive bubble. That bubble is a completely different, way larger surface, but it still shares the exact same boundary loop, the hula hoop itself. It's this fascinating little quirk of 3D geometry that the math absolutely has to account for. All right, Section 4, the math of Faraday, bringing it all together. Okay, we are now fully armed and prepared to tackle that scary block of equations 1.1 through 1.4, and we are not going to get lost. Let's slow it down and trace the logic together. Step 1 is our base law. Equation 1.1 tells us EMF is the negative rate of change of magnetic flux. Mathematically, that's epsilon equals negative d phi m over dt. Now, step 2, we expand the EMF. Remember those margin scribbles? We replace epsilon with the line integral of the electric field, which gives us equation 1.2. Step 3, we expand the flux. We replace phi m with the surface integral of the magnetic field, landing us at equation 1.3. And that brings us to step 4, the grand finale, equation 1.4. We just plug those newly expanded terms right back into our base law. The line integral of the electric field equals the negative time derivative of the surface integral of the magnetic field. Boom. You just read advanced vector calculus and you understood exactly what it's doing. And finally, section 5, static versus induced fields, resolving a textbook conflict. Now, if you've got some prior physics background, you might have spotted a pretty glaring contradiction here, which the textbook actually tackles head-on in example 1.1. The text asks, how can the closed-loop integral of E.dl be non-zero for Faraday's law? Is it not at variance with Coulomb's law, which requires it to be zero? And honestly, it's a fantastic question. Electrostatics clearly tells us that if you move a charge around a closed loop and bring it right back to where it started, the net work done has to be exactly zero. So how is Faraday's law even allowed to work? Well, the textbook provides this really elegant solution to resolve the tension. It distinguishes between two completely different types of electric fields. First up, we have static electric fields, or E sub s. These are created by static charges, and their line integral in a closed loop always equals zero, no exceptions. But then we have induced electric fields, or E sub d. These are the fields created by changing magnetic fields, which is the exact phenomenon Faraday discovered. And for these induced fields, the line integral does not equal zero. In reality, the total electric field is just the sum of both, E static plus E induced. Faraday's law works perfectly because it relies entirely on that non-zero induced field. Mystery officially solved. So we've gone from deciphering frantic margin scribbles to untangling the mysteries of electromagnetic induction and complex line integrals. But before we wrap up, I want to bring all this dense math right back into physical reality. Take a second and look around the room you're sitting in right now. The electricity powering the screen you're watching this on, the lights above your head, the literal fabric of our modern electrical grid, it almost entirely relies on spinning magnets near coils of wire. It relies on this exact math. It's wild to think about. So, what else in your daily life is driven by a simple changing magnetic flux? Keep thinking about that and keep exploring. Thanks for joining me for this explainer, and I'll catch you next time.